Section 6.2 Capacitors. A capacitor consists of two conducting plates separated by an insulator or dielectric, and you can find it in this graph. And there are two plates, and normally it's metal plates, and each with area A. The distance between the two plates is d, and between the plates there is a dielectric with permittivity epsilon. In many practical applications, the plates may be aluminum foil, while the dielectric may be air, ceramic, paper, or mica. And this graph stands for a capacitor. Capacitance is the ratio of the charge on one plate of a capacitor to the voltage difference between the two plates, measured in farad. And from the graph, we should know on each of the plate there are charge, and the quantity of the charge is Q. So we can calculate Q equals C multiplied by V, where the V is the voltage of the voltage source. So C is the capacitance. For capacitor, we can calculate the capacitance using this equation. C equals epsilon multiplied by A divided by D. And there are three factors determine the value of the capacitance. The first one is the surface area of the plates. The larger the area, the greater the capacitance. The second factor is the spacing between the plates. The smaller the spacing, the greater the capacitance. And the third factor is the permittivity of the material. The higher the permittivity, the greater the capacitance. Now you can see the circuit symbol of a capacitor on the slides. For the graph A, it is for fixed capacitor. For the graph B, it is a variable capacitor. Because capacitor is a storage element, so it can be charged. When V is greater than 0 and I is greater than 0, or V is less than 0 and I is less than 0, and we should know for this situation the capacitor is being charged. And if V multiplied by I is less than 0, that means the capacitor is discharging. Capacitors are used to block DC, pass AC. DC means direct current, and AC means alternative current. And capacitors are used to shift phase and store energy, start motors, and suppress noise as well. Those are the graphs of real capacitors. The first one is polyester capacitor. The second one is ceramic capacitor. This is the relation between the current I and the voltage V of a capacitor. For linear capacitor, I equals dq over dt. And we put the equation of Q inside, and we get I equals C times dV over dt. So the current I is in direct operational to the dV over dt. And from this equation, we can get another equation. Vt equals the reciprocal of C multiplied by the integral from minus infinity to t with respect to I tau multiplied by d tau. And we get Vt equals 1 over C multiplied by the integral from t0 to t I tau multiplied by d tau plus Vt0, where Vt0 is the voltage of the capacitor at t equals t0, and we call it as initial condition. And then we can calculate the power absorbed by the capacitor, which means P equals V multiplied by I equals C multiplied by V multiplied by dV over dt. And we can calculate the energy stored in the capacitor as well. W equals the integral from minus infinity to t with respect to p tau multiplied by d tau equals 1 over 2 multiplied by c multiplied by v squared. And finally, we get the equation of the energy stored in capacitor. W equals 1 over 2 multiplied by c multiplied by v squared. And we can also calculate the energy with the charge stored in the capacitor, which is W equals Q squared over 2 times C. Okay, now we should know the important properties of a capacitor. The first one, when the voltage across a capacitor is not changing with time, that is DC voltage, the current through the capacitor is 0. That means a capacitor is an open circuit to DC. However, if a battery or DC voltage is connected across a capacitor, the capacitor charges. 2. The voltage on the capacitor must be continuous. That means the voltage on a capacitor cannot change abruptly. For example, the waveform in the graph A of the voltage is allowed to a capacitor, while the waveform of the voltage in the graph B is not allowed for a capacitor, because the voltage in the graph B is not continuous. 3. The ideal capacitor does not dissipate energy. It takes power from the circuit when storing energy in its field and retains previously stored energy when delivering power to the circuit. So it does not dissipate energy at all. 4. A real non-ideal capacitor has a parallel model leakage resistance. The leakage resistance may be as high as 100 mega ohms and can be neglected from the most practical applications. As you can see the circuit in the graph, there is a leakage resistance in parallel with the capacitance. However, this resistance is very, very large. So normally, we don't consider this leakage resistance at all. This is the end of this section.